Great. Hello, everyone. Welcome to another quantum computing class at Hackaday. This is our session 15 for the Hackaday community. And also 7 sessions ago, we started inviting a lot more other communities. So welcome and welcome back to people who have been joining. So always a reminder for people who are joining for the first time. We've been doing this class every Sunday, and all of the materials and recording slides are posted on the Hackaday Introduction to Quantum Computing project. And every Sunday, I spend about 30 minutes to 1 hour discussing one topic. Thanks, Nathan, for posting the link there. And if people can also mute themselves, that would be helpful. Thanks. The materials that we use in the class, we refer to the Microsoft Q-Sharp documentation, and we also use the quantum katas for exercises. So today we're going to also do a katas. Actually, a kata is singular. So this people have seen almost every class now, that we have this landscape that tells us where we are and what we're doing for the class. And we use the Q-Sharp as a way to connect from the concept to coding algorithms. So previously, we have done quite a few algorithms that's based on superposition and entanglement. So like teleportation, superdense coding, those are using entanglement for interesting communication purposes. There are a lot of other algorithms that are using all of these properties. So if we put entanglement and interference into the same algorithm and use all of these behaviors from quantum computing effects, that can be very interesting and powerful. So today we are going to look into a particular algorithm called Gruvers Algorithm. Before that, I have this reminder here. We have seen in some previous classes the Deutsch algorithm and Deutsch-Hose algorithm, where we did look at a case where interference was very important. So namely, when you can have interference happening when you introduce a negative sign, you can distractively interfere with some other states and reducing the probability of that state being in your measurement result. So this is really useful if you use this interference behavior in your setup. You can extract information efficiently. So this is Deutsch's algorithm. We're not going to do. I don't think we need to do another coding exercise, although there are quite a few on the quantum katas. So if you are interested, and I definitely encourage you to go to the kata and try the Deutsch algorithm and Deutsch-Hose algorithm using the katas. And if you missed the conceptual class about this, we have that in the previous list of classes you can watch the recording for. But we're gonna use today's class on Gruvers algorithm because that's a useful algorithm. Is also one of the most famous algorithms that was invented or came up with by the Indian-American computer scientist Groover. And we did spend session 8 on discussing the topic and concept about this, but we would do a revision today. And if you want to see the previous one, go to the May 17th session. This one, as well as the Shor's algorithm, are the ones that you can actually use for some applications, whereas Deutsch's algorithm and Deutsch-Hose are more academic algorithm that were invented early on in the development of quantum computing. So they do not have real use cases, but they are very useful in terms of learning and understanding. We can also use Groover to gain some intuition and understanding of using superposition, interference, entanglement in the algorithm setup. So broadly speaking, if we just zoom out, not looking at the details, what this algorithm does is trying to search for an item in a unordered, unsorted list. And it's like doing this selection here, it can increase the amplitude or probability of the item that we're looking for. And it is consisted of a couple of boxes that we need to run in iterations. The Groover's algorithm, you can do you can use it for searching an item, and you can do that using classical algorithm as well. And classically, if you want to search an item in a list, then you may have to, if you have n bits, you may have to run your algorithm up scaling with 2 to the n. But for Groover, the scaling is 2 to the n over 2, so square root of 2 to the n. Then at first, if you have a small number of bits, it may not be a speed up. So this is something that we have to keep in mind, that this algorithm would be advantageous once we reach certain qubit numbers. So it's like this race between a supercomputer and a quantum computer, where at this region, so maybe a small number of qubits, you can just do it with a classical computer. There's not much reason why you would use a quantum computer to run it. But when the number of qubits gets really large, then that's when this Groover's algorithm really can take off. So we don't quite know the exact number that's needed, where this will occur. It depends on a couple of things. So the classical versus quantum, these scaling, we don't exactly, these are the scaling factors, but we don't exactly know the factors for the supercomputer or quantum computer because we don't quite know what would be the best kind of supercomputer and the best kind of quantum computer yet. And of course, we're still building quantum computers, and there are so many different types of architecture. So this, how much running one of the algorithm running it once would take, we don't exactly know. And we don't exactly know how many numbers of qubits that we would need to see this crossover. But then we know that it's going to be a large number. And then if we look at smaller numbers, we have to come up with a lot more algorithms to really show at the low number, can we come up with some useful, interesting algorithms that could have quantum computers being more advantageous. So this is definitely, all of these are, both the hardware and the algorithms are depending on all of us when we are doing quantum computing development, both in terms of software and algorithm development, as well as the hardware. I did also make a little plot just to show this concept here. It's not that for yeah, of course, if we look at the scaling factor, Groover is square root of 2 to the n. Classical is 2 to the n, and it seems that Groover would be faster, but then we don't know what the prefactors are. So if you want to see how this scaling goes, and you can put just fictitious factors in front of them. In this case, I'm putting b equals to 10 and a equals to 1. And that's just a fictitious guess, because that really depends on how good your hardware is and how fast intrinsically your computer will run one iteration of your algorithm. So yeah, just some additional emphasis that I didn't mention in the last class, and also some food for thought there. Okay, so when we are building a algorithm, we will need to have this oracle when you want to use interference in your algorithm. This oracle is like a black box. We have learned about this in session 7 on May 10th. And we use the Deutsch-Holzer algorithm to understand concept of quantum oracle. So for people who have missed that, definitely go to that session. We won't be repeating it. So in short, when we are building a quantum algorithm, we need these oracles that functions like inputs of another part of the algorithm. And for Groover, we can build several different types of boxes depending on which item we're searching for. For example, the black box for 111. So if we just have 3 qubits that we are interested in, we can just arbitrarily say 110 is what we are looking for. And the label of that, so y of f of x, we expect it to be 1, and the other ones would output 0. In order to build a black box that would pick out 110, we need to construct this kind of controlled gates. So if you remember, the controlled NOT gate just involves 2 qubits, and the first one is the control, the second one is the target. And only when the first one is 1, the second one would flip from 0 to 1 or from 1 to 0. If you have 3 qubits, this is called a CC NOT. It is also called a Tofoli Gate. It has the first 2 qubits being the control and the last one being the target. Again, you can only flip this one when the first 2 are both zeros. Now you have more qubits, you just add up this control bits. So the requirement of this control gate is that all of the other qubits need to be ones when your last one can be flipped. So then this means that 110 wouldn't work unless you put these flip gates around it. So especially this one, because that would flip from 0 to 1, then you can change this qubit here. So that's how you set up a black box. And I forgot to mention that oracle also needs to be set up in order to make a unitary operation. So that's another need for setting up oracles. If these all sound very new to you, definitely go back to the previous sessions. So similarly, you can build other types of other black boxes, still using 3 qubits as examples. For 010, you will have the X gates set up on both the zeros. If you have already the 111 you want to label, then you don't need to give it a flip, because this already can flip the last qubit. So this is the part that you need to set up first as your oracle for Gruvers algorithm, which would then label or mark your item on the list. If you look at the complete diagram for Gruvers, again, using just 3 qubits, because that's not too many qubits and not too few qubits, we can still do some calculations by hand if we get lost. This first part is making everything to equal superposition. When you start with just zeros in your system, you will have this maximum amplitude for 0, 0, 0. The other options are not there. But if you scramble them with the H gates, they would make all of your qubits into a superposition of 0 and 1s. Then you have all of these possibilities in superposition, and they all have equal amplitudes. That's what this part does. Then the second part is the black box, the oracles that I already mentioned, introduced. What this does is if you want to set up a 101 black box, you would put the X gates around your second bit because your second bit is 0. And then what happens in here is then this very last bit is used to introduce a negative sign. So this negative sign would then be scrambled into your whole entanglement or this controlled setup. This negative sign will be introduced to no one else except the one that you label. So the 101 now gets a negative amplitude. This would be very, very useful in the next few steps. Look at the second part of the algorithm, this another box. This is like the oracle earlier, where you have now the X gates for all 3 of the input qubits. And because of your experience with the earlier one, you know that if my qubits are all 0, then they are being flipped, and then they can control the very last bit. So this one allows you to get the 0, 0, 0 to have a negative, just like how this one got a negative for the 101. This one would give a negative to your 0, 0, 0. But what happens when you have an extra incoming qubit that had a negative sign introduced? What this one does is allowing all of these amplitudes to flip their signs. So now your 0, 0, 0 becomes positive and all the rest becomes negative. This is the use of this very last qubit here, is purposely introducing this negative sign. And then the next bit is even funnier, is that not only do you have this box with all these X gates, you also have some H gates on both sides. And what does this do? This both sides you have H gates will actually allow you to flip all of the amplitudes over this mean value of all of the amplitudes. So this is maybe a little, if this is the first time you see Gruvers algorithm, maybe a little mind-boggling. How is it allowing you to flip over the mean? So the H gate, remember that when we look at the single qubit gates, when we introduce H, it is allowing you to go from 0 to plus and 1 to minus. And in effect, it is also flipping your states around the mean. If you have two H gates around both sides of whatever that's in here. And I will show you a little bit more about this when we do the coding. Oh, actually, I do have this slide here coming up. Yeah, let me show this then. So imagine you just have one qubit. You would just have 0 and 1 as your basis, and you have an arbitrary state. So we just saw that whatever is in this box is allowing you to have a negative sign introduced. And that means you're rotating around this 0 axis. And that's what this whole box does when you have that negative sign introduced. Now, if you apply this, when we have just one qubit, just one H gate on both sides, eventually your state is going to end up here. And that is a flip over its mean value. And this is just looking at one qubit. So anything that is flipping around the z-axis or flipping around the 0 state plus 2 H gates on both sides will allow you to flip around the mean eventually. So this is only one qubit, and we're looking at the block sphere, and it's an easy visual tool to think about it. But now if you have additional qubits, then you're adding up the dimension, and humans, we won't be able to visualize more than 3 dimensions. But the truth is, it's just adding more states, and it's the same principle. You are flipping over all 0 states in this box. And then in this whole box here, you're flipping over all of the possibilities mean. So this is really freaky. I really like this algorithm. So that's what it does. It's very useful because now if you repeat this 2 boxes over and over, you would be able to continuously increase the amplitude of the one that you marked. So flip over 0 and flip over mean a couple of times. So it turns out that the number of times you need to do this iteration is square root of 2 to the n, as I introduced at the beginning of the class. So if you just have like 3 qubits, you don't have to iterate so many times. But when you have lots of qubits, your classical computer is gonna scale with 2 to the n, but then Groover can scale to square root of 2 to the n, much fewer steps than classical. And that's why it's useful and gives us that speed up. And yeah, and even if you just have a few qubits, you don't also even have to use any computer. You can just use your brain. And I think earlier, I do want to mention that I put the math here. If you want to check what's happening, feel free to just write out, since we only have 3 qubits, you can write out every single state and see what happens. And then you will see this negative sign will be introduced to all of the possibilities. But then because your first 000 already has a minus, it becomes positive. The rest of it will be negative. So definitely try out the maths. I will highly recommend that. So let's do some coding. We have the quantum katas and a lot of samples on Gruvers algorithm. What we're gonna use today is the one in the kata, this one. So the one that sets up the Gruvers algorithm. The other ones are using the algorithm, and there are some really fun ones. Like this is to use the Gruvers algorithm in another setup. This one helps you visualize it by doing a graph coloring example. This one is a fun write-up by my colleagues on decorating Christmas trees. It's like you want to choose, you have a rule of how many ornaments you want to put on each layer of the tree, and you need to have efficient algorithm to automatically select where to put what. We also have like a analogy by my colleague about Santa Claus trying to find the right gift for the kids from the bag, but all of the gifts are randomly ordered, and he needs to have a algorithm to find the exact right gift. So that's the kind of examples that Gruvers can help. So let's go to the katas. I would show both of my screens now. Do the Control+ to hopefully increase the words for you. And you can also do it on your screen. So the Gruvers one is this Gruvers algorithm folder. Now we will use the Jupyter notebook. And also, I think we probably can spend a couple classes on Gruvers. If we don't get to finish everything, we can continue next time. There are so many interesting work around that. Hopefully, Jupyter is not too slow. I mean, Binder is not too slow today. So when you open the Gruvers algorithm on the katas, this is the non-installation option on Jupyter Notebook on the Binder. Feel free to read the earlier ones when you have time. So we just gonna go to task 101 here. We are given n qubits as our arbitrary states. So all of our input qubits. So all of the first ones. But in this case, we have n, not just 3. And that's also, by the way, why a language like Q# is powerful, is that we're not limited to a small number. We can scale it up to any number of qubits. And then we have a arbitrary state y, which is our very bottom one. It says, flip the state of the target qubit, apply a X gate to it if the query register is in the all one states. So this is basically saying that we want to label our all one state as the one we are looking for. So if the query register is in the state all 0, leave the target unchanged. If it's 1 plus all 0, leave unchanged. So if you have any 0 in your state, leave them unchanged. Only the all ones, you flip the target. So we just set up like what this shows here. And don't worry about this, this is for later. So this over here is, so this Oracle all ones test is asking us to build exactly this Oracle here, except it's the all one state that we want to do. So that's actually very, very simple. We use the Control X, exactly like these, Control X, and we make all of the query register as our input. And then the target is the target. So that's it. Because this one is basically the easiest one. Oh, did I miss anything? Oh, target. This one is the easiest one because you don't have to add any additional X gates. But if you are asked to do like the later ones, that you actually have to flip the 0 states to the 1 in order to have this control operation working. We're gonna skip the next 3 oracles. Those are for you to do as homework. Those are just setting up different types of oracles. And then we should go build up the Groover iterations. Now is asking to do the Harama transformation. So is this part of the algorithm here is the flip over mean. So this is asking to build using the n qubits, our registry qubits, so all of the top ones, and apply the Harama transformation to each of the qubits in the register. If the register started in the all zero state, this operation will prepare an equal superposition of all 2 to the n basis states. Sure. So yeah, okay, I was gonna talk about this, but no, it's the next step. So this is nothing but setting up these Harama gates. Actually, just these ones, the inputs. So again, you're gonna do the Harama. We have a very convenient command called or operation called apply to each. So that reduces your writing. You don't have to do like 3 lines, because you can write like for all the qubits in your register do a H, but we do have a command called apply to each. And you can just do the H gate to register. But here is asking for an adjoint. We have also a very convenient way to do that. You can just put A as adjoint. We also have a control type. So if the question asks us to build control, we would put the C there. And how do we find out about what these all mean? We can go to the Microsoft Quantum documentation page. That's where you can find all the APIs about Q#. So if I put apply to each, there are apply to each without anything at AC or AC. So this is the one we're using, and you can read about what this operation does. So A here is just the adjoint, and we talked about adjoint some classes ago. So that's what you need for that step, this here. So the next part is fun. And I also kind of learned about this part from the katas, because earlier I didn't realize this, and this is really cool, that there are actually many ways you can introduce the minus sign. The one that I show you was kind of because is very similar to this part. So I was naturally showing you this option where you have all of the control ones you need to make all of your control ones to be 1 and the last qubit to be target in order to introduce the minus sign from the last qubit. However, you have other ways to do that. You don't even have to use this very last qubit in this reflection over mean operation. Remember, in our single qubit gates, we have seen the X. What X does is flipping from 0 to 1, 1 to 0. But we also have this Z gate. It intrinsically introduces a minus sign, is rotating around the Z axis. So you're giving your second element this negative sign here. And you can just do this to introduce that minus sign. And this is what this conditional phase flip is asking us to do. But you can also build this one if you want. So this one is trying to give us a hint to do this kind of operation. So let's do their way. So the first thing is that you need to set up these X, use this one now. Set up these X control, the X gates, and then the controlled Z gate. And this algorithm is nice. This whole kata is nice because it's introducing quite a few algorithms, or quite a few operations. So there's something called within apply. So that means it's kind of exactly like what this does is within these things, you can apply this here. So you can do within, again, apply to each. And again, it's asking for the adjoint version. So we put an A there. The X to the register. Now in here, we are doing the Control Z. So how do you write in the most efficient way that you want the last qubit to be your target, the rest to be controlled? Turn out there's something in Q# you can do that, and that one is called the tail. If you look at the API, the tail function returns the last element of the array. And opposite to tail is most. So most is all the rest of the qubits, and tail. And I think I might have left out, I think we need to have the X for these ones too. So that's what this is helping us to set up. So that's how you can do a conditional flip to, all this does is introducing to you, I might have left some brackets, oh, good point. Okay, so I'm using this operation without opening the right package and is at the namespace. So you actually have to open it here in order to use the library. So that should do it. The very last step is allowing us to put everything together. So doing the iterations. So it's exactly like what we set up on the left here. You just do, because oracle here is already introduced, and this is your oracle. You write oracle register. And then you have the Harama. And we had the Harama transformation defined here. Then we have the conditional phase flip. The last step is the rest of the Harama gate. So we do this again. That should do. So this is how we set up step by step. And see that oracle here, if you just have any oracle setup, then you can interchangeably put any oracle that you want in this step. And also we have no limitation of the number of qubits, because n, it can be any number. So this is just a visual guide for a small number of qubits. We can draw a diagram, but when we want to scale it, it really needs the this kind of high-level language for us to represent a scalable algorithm. So yeah, I will let you finish the ones that we skipped and the last bit. And next class, we should probably try something else around Groover. So frequently asked question, all of the recording is posted on Hackaday on the project and also on YouTube. And I have a few minutes I can look at in the chat if there's any question. But if any question comes up during the week, you can post on the Hackaday project as well. There is a comment section at the very bottom of the project. You can post questions. Okay. So Tony asked something earlier. Yeah, he joined the series late. Yeah, okay, thank you. You can go catch up, look at the recordings. David says, did anyone ever find the answer to why the word oracle was? Yeah, good question. I actually even have a certificate for people who answered this. If you find the answer, just post it on Hackaday or tweet it. And yeah, I think it's quite funny that oracle is used. Adam says battleships at some point. I don't know what he's referring to. Yes, Christmas, Quantum Christmas is fun, but we're in the wrong season right now. So Adam says you can break down Groover's algorithm to count the number of solutions that exist. I don't quite get that comment. Would you mind elaborating that? I see. Battleships is part of Matrix. All right, if there's no other questions, we can come back next week. And I will stop recording and post this on the project. Oh, there's one more comment. Oracle is more like Sumit says, a single unit that reveals a hidden knowledge in Greek mythology. Originally, Oak Ridge computer, when it started in computing, essentially Oracle in algorithm is same. Is Oak Ridge the origin of first using this name? That would make sense. Ruksha asking to summarize about this class. So we have first page. I will start with this. That this is a weekly class. Every week we discuss one topic and we try some coding also. Every week I post a new comic about the topic that we're gonna discuss, and it hopefully gives you some intuition too. We use the Q-sharp documentation and quantum katas as our references. So yeah, it's free and anyone can dial in and watch and try the katas together. And this is on Hackaday U as well as Microsoft Reactor. Past sessions are all recorded and posted online. You can find everything from the class link that people also posted in the chat. And thanks everyone for doing that. Yeah, thank you everyone. Someone asked about Astro Quantum. Yes, Sumit.